Welcome to this talk. My name is Phileas Dazeley-Gaist. I'm an applications developer here at Wolfram Research, and today I'm going to tell you about Wolfram notebooks for GIS coursework. Let me start with a brief overview of what this talk is about. We'll discuss how to manage and represent geographic data in Wolfram Language, then how to extend existing functionality for GIS in Wolfram Language through external services like APIs, and then finally we'll go over some case studies, some examples of how you might extend the functionality for GIS, build your own GIS functionality using built-in functions and symbols. I'd like to acknowledge also that this talk is the result of a collaboration with Gordon Longsworth, who's the director of the College of the Atlantic GIS Lab, so thank you, Gordon, for all your help in putting this together. In the Wolfram language, there's a large amount of geographic data that you can represent using information from the Wolfram Knowledgebase. The Wolfram Knowledgebase is a large collection of data about the real world that is curated by Wolfram and built straight into the Wolfram language. You can read a little bit more about it on our website in the core areas/knowledge base section. But the core idea here is that we want to be able to bring in information about the real world and use it in computation. And Wolfram Language has access to many built-in curated geographic data sources and computable geographic entities to do this. So let's take a little bit of a deeper look at what these are. So first, let's talk about named entities. Named entities in Wolfram Language represent named things that the language knows about and can perform computations with. The easiest way that you can start to discover these is by going into an empty cell and typing control plus equals. And this will open a little input that lets you type in some text. So for instance, United States, corresponding to an entity. And I can even leave a typo in here. And the parser, when I evaluate this code, will successfully, in most cases, be able to match to the closest entity. And in this case, it correctly matched to the United States. So now, if I accept this, I have a little entity that I can use as inputs in functions, or I can extract data from, and this is a computable object in the language. So what can I represent this way? Well, in terms of geographic data, I can represent many different kinds of things. I can represent countries, cities, mountains, lakes. The data don't even need to be geographic data on Earth. It could be geographic data on another planet or on the moon, as here with this entity class. So this is a group of entities that captures the locations of the Apollo moon landings. So I just mentioned an entity class. An entity class is a group of entities. It's an entity that contains other entities. And if you want to retrieve the list of entities that are part of a particular entity class, you can simply say, I'd like the entity list of the argument, the entity class that you like, and you get as a result a list of entities that are part of that class. I mentioned some entities for geographic representations, but entities are also really useful for representing all sorts of non-geographic things like people, plants, animals, historical events. This is a really rich area and feature of the Wolfram language, and I encourage you to explore it on your own time because many kinds of information are just built in and very easy to import and play with and build examples from. To get information about an entity, we can ask for one of its properties, like this. Here I have an entity representing an island, and I can ask for its area using this open-close square bracket notation the same way that I would supply an argument to a function. And I get as my output the area of that island. I can get the full list of properties that are available for an entity by using the properties property. So here, for the same entity, I'm asking for its properties, and I get as the output a list of property entities that I can use as arguments over here to get the associated data for any of these. So I could get the total area, I could get the country that it's in, I could check if it has a polygon, etc., etc. I should note that these properties are associated with the entity kind. The fact that this is an island entity means that it has these properties. And so sometimes there will be properties here that aren't associated with any data for a particular entity. So Mount Desert Island might have a polygon, but it might not have information about alternate names, for example. This is just sort of a standardized way that we represent entities that are islands. So in many cases, you'll just want to extract the information that's known about an entity. And the way you can do this is like this, for example. You would take the entity, ask for a dataset representation of the entity, so key value pairs for everything that is available for that entity. This will contain potentially some missing values, so we delete the missing values. And then here, just for visualization, I've added a clause that says show me only up to 6 items at a time so that the resulting dataset fits in my window. And so we can scroll in this dataset and we can see what's available, what kind of information is known about Mount Desert Island. We know the polygon that represents the sort of the outline of the island. We know what kind of entity types it corresponds to, what country it's in, what its area is, the highest elevation on the island, the name of the highest mount. Even have a nice little picture. So this is all information that is associated with that entity. I said earlier that entities are computable, and what this means in practice is that you can use entities or data from entities as arguments in functions, and the Wolfram language will try to interpret the information as sensibly as it can. So we'll see many examples of this pertaining to geographic functions a little bit later, but for now, just so that you can get a conceptual grasp of what's going on, what this looks like, here's an example where we make a satellite view cutout of Mount Desert Island using a blank background. So I take my Mount Desert Island entity, and we're going to ask for the geopolygon that corresponds to that entity, and it will know, based on the fact that this is a geographic entity that represents an island, that it should fetch the polygon that corresponds to that entity. And then I can wrap this into a geographics call where I'm asking for geostyling as satellite styling, so that the contents of the polygon will be satellite imagery, and I can ask for no geo background, and when I evaluate this code, it will return this nice cutout of Mount Desert Island. As I mentioned earlier, there are many different kinds of geographic data that you can represent as entities in the Wolfram language, and the best way to get a sense of the scope of this is to head to the Geographic Data Wolfram Guide page in the documentation. In this page, you'll find a long list of many different kinds of entity types, and by clicking through them, you can learn more about what's available, what kind of information they encode, and how to use them in your code and your projects. Wolfram Language also offers special functions to access data from the Wolfram Knowledgebase. These include curated spatial data functions like geoelevation data, or weather data, wind vector data, earthquake data. There's even a volcano data to get the times and locations of volcano eruptions. So how might you use these functions? Let's look at a few examples. In GIS context, you will very frequently need to represent elevation data using what's called a digital elevation model. And in Wolfram language, in many cases, you can do this in a single line. Here's an example in which I'm setting the result of evaluating this geoelevation data function with as its first argument the Mount Desert Island entity and a couple extra options that specify the projection and the unit system that I'd like. And then I can simply use this resulting quantity array in a relief plot function call to represent the elevation of this landscape. And here I'm specifying some additional options, again, to get a legend and to plot the island the right way up. I could also make a contour map, and again, with any of these functions, there are many additional options that I could use to fine-tune and really customize the output that I get. So I could specify individual contour lines to use, or a number of contour lines. I could change the color function. I could add different kinds of labels, and so on. We also have wind vector data, which you can use to represent wind vectors for a particular time and location. And we're going to use this in this example to make a stream plot map, a geo stream plot of wind vectors from Maine from yesterday. So how would we do this? First, we need a grid of geographic positions, something like this. And in fact, so that it's slightly more readable, I'm just going to make it look like a matrix, so you get to see sort of what this looks like. This is a matrix of geographic positions. And the way that this is made is first we get the geographic bounds of the state of Maine. Then we're going to subdivide those bounds into an 8 by 8 matrix. And then we're going to make each of the cells in that matrix. That's why we're applying at level 2, because it's a list of lists, because it's an array. We're going to turn every cell of that matrix, every latitude, longitude, into a geoposition explicitly. And the result is this. Okay, so that's the first step. We have all of the positions at which we want to find our vectors. Then we need to actually fetch all of the vector data. So what we do, very similarly, we say for every cell, we're going to map over every one of these positions the function wind vector data to fetch for that position for yesterday the downwind geovector in the metric unit system. And we get, as a result, this long list of geovectors, and I've randomly sampled a few of them here, so this is what they look like. You get a geovector object, which contains a geoposition, and then the speed and angle of the vector. And we can simply supply this main wind vectors variable as an argument to GeoStreamPlot to get a plot that represents the winds through Maine from yesterday. And I've added a region function over here to make a sort of cutout of Maine and include only the wind vectors that are inside of this region. Here's one more example. Suppose that you want to plot locations of earthquakes that fit a certain criteria. One way you can do this is with the earthquake data function. So here's an example in which we're looking for magnitude 6 to 9 earthquakes that happened in 2024. So all earthquakes between magnitude 6 and 9 that fall between these two dates, that were recorded between these two dates. We assign the result to this big earthquakes data variable. The result is this data set. And the data set contains the following fields, which include position and magnitude. And we can just extract these fields and feed them to a GeoBubble chart like this, and get this nice visualization, this interactive geographic bubble chart where we can hover over different earthquake locations for earthquakes that occurred in 2024 and see what their magnitudes are. Aside from geographic data from the Wolfram Knowledgebase, we can also represent arbitrary geographic data which we generate or import from external sources. Wolfram Language offers many ways to represent and process arbitrary geographic data, and these representations can all be exported to many standard GIS formats like shapefiles, GeoJSON, KML, and so on. Perhaps the simplest kind of geographic data are geodetic positions. So in Wolfram Language, the way that you would define a geodetic position is with this geoposition function, which takes in a list containing the latitude followed by the longitude. So if I assign the result of computing this function to this little variable, I can ask for geolist plot of this variable, and I get the position of Null Island represented on a map. Sometimes we might also like to use coordinates in other coordinate reference systems, and we can change between coordinate reference systems using geogrid positions. Here's an example in which I'm going to represent a position in the Olbers projection. So this is the coordinates in the Olbers projection, and here I'm just specifying this should be interpreted as an Olbers projection pair of coordinates. And then I can simply ask for the geoposition that corresponds to this geogrid position to recover the geodetic position. We can also represent lines or polygons geographically. Lines are just going to be considered lists of points, and polygons are just going to be lists of points that we draw as filled shapes. Let's demonstrate what this looks like. First, I'm going to start with a variable cities, which is just going to be a list of entities that correspond to cities. And then if I want to plot a line on a map that represents the line between these cities, I can ask for the geopath between the cities of type geodesic. So here, the second argument specifies the type of line that I'd like, and I have the option between geodesic, run line, and great ellipse. And then I wrap this geopath call in geographics, and it will return a map, a geographic representation of this path. And here you can compare the differences between the different kinds of lines. Now, because we used geographic entities directly, we never had to deal with geodetic coordinates. And if we'd wanted to, we could still have extracted those coordinates using something like entity value. So here I'm saying I'd like the entity value for the list of entities, cities, and I'd like the position value. And I'm assigning the result to city positions. So why am I showing you this now? It turns out that you can't use this strategy of just supplying cities as an argument to the function that we're going to use to make polygon representations, because there's an ambiguity where if I ask for the polygon represented by a list of 5 cities, am I asking for the union of the outlines of polygons that represent the sort of the shape of the city? Or am I asking for a polygon in which each point is the position of the city? Because of that ambiguity, we ask you to use geodetic coordinates directly. And so this is why I'm getting these city positions over here. So here's how it would work. I would ask for the geopolygon that corresponds to the positions specified by city positions, and I'm going to wrap it in geographics again. Now, the third argument here is the same argument that we had above, where we specify the kind of line that we'd like. And then the second argument specifies which kind of polygon we'd like. By default, this is going to be the smaller area, but there's 2 types of polygons that you can draw from the same list of points on a sphere. There's the smaller polygon, which is usually what you want, and then the complement to that polygon, the larger of the 2 areas. So the rest of the globe, basically. We also have functions to represent hemispheres and terminators. So suppose I'd like to represent the hemisphere whose center is my current position. I could do this using geohemisphere of here, which gives my current position based on my IP address, and wrapping this in geographics. I could also get the boundary between the hemisphere that is centered at a particular point and the other hemisphere using geohemisphere boundary. Or if I'd like to know which half of the Earth is currently daytime, I could ask for the day hemisphere. I could also ask for the night hemisphere to get the hemisphere where it's currently nighttime. And I could specify a different time here as the argument now to get the day hemisphere at a particular date and time, for example, or the night hemisphere at a particular date and time. Finally, I can also get the terminator between the day and night hemispheres for a particular time using day-night terminator. And you see the syntax is the same for all of these. I'm simply asking for the terminator or the hemisphere with an argument that specifies how to get that information, and then I'm asking for the geographics to get the result. We also have many geographic visualization functions. We've seen a few examples of them earlier with calls to geographics and geolistplot, though there are others as we'll see in a moment. Geographics is the most flexible and general of the geographic visualization functions in Wolfram language. It can be used to represent almost anything geographically, but often there'll be a more specific, a more specialized function that lets you get to where you need to be a little bit faster. So here's just an example using geographics to highlight the flexibility of the function. Here I'm going to make a map of Europe in which European Union countries are filled in with their national flags. So first I'm going to set, using with, a local variable countries, which is set to the result of this entity list call, so a list of entities corresponding to countries in the European Union. Then I'm going to ask for a geographics, so geographical representation of what comes next here. I'm going to explain this in a moment. I'm going to specify that as the background, I like to have country borders, and I would like the land to just be blank space. And so this thread here is, we can understand this in three parts. First, I'm applying this polygon call to every country. So I'm getting the polygon for each country. Okay, then I'm getting the flags for all of these countries, and I'm applying this geostyling command using map to each of the flags. So this is going to give me geostyling with the parameter geoimage of the particular flag. And then I thread them together to get pairs of geostylings and country polygons, things that would look a little bit like this. And then the result is just this list where you have multiple geostyling commands. So if I represent this, if I send this to Geographics, for example, I would now be able to show a map of Austria with the Austrian flag filling the country polygon. This is what we're doing here. We're just doing it with more countries and more stylings. And the result is this nice map. In many cases, you don't need to do anything quite so complicated. So maybe you just need to plot a list of locations. You'd use something like GeoListPlot in this case. So GeoListPlot can take a list of cities and it will just plot them as points. In this case, I'm saying I'd like callouts for them because I want to label them nicely. And so I'm going to map the callout function that takes in the city argument, and then as the value, I'm going to style the name of the city so that it's a certain size and make sure that all of them are visible. So I put this in as my first argument, and I add a few styling parameters, and it gives me this nice result. And you'll notice it picked a geoprojection automatically based on the points that I gave it, but I can also specify one manually if I'd like something else. I can also plot scalar values at locations using something like GeoBubble chart or GeoRegion value plot. So here's an example in which I'm looking at population sizes of countries in Asia. First, again, I make a local variable corresponding to a list of countries in Asia, and then I make a list of rules that pair the region entities to the population values and submit this to GeoBubble chart. And the result is this nice interactive visualization where I can hover over specific bubbles to get the population size for a particular country. I might also want to just fill in the countries with a particular color based on this population value. And so I can do this using GeoRegion value plot. This is what it would look like for the list of population sizes of countries in Africa. So here I'm again setting a local variable, and then the syntax is the same essentially, except that I've replaced GeoBubble chart with GeoRegion value plot, and I've set a specific color function over here to choose a particular gradient. We can also do things like contour plots or heat maps. Earlier I showed this example in which we constructed a digital elevation model of Mount Desert Island. Here I'm fetching a digital elevation model for the 40 square mile area around the Manicouagan Reservoir in Canada, and I'm specifying that the digital elevation model should be made out of geopositions, which encode elevations here rather than as an array. And once I have the data in this format, I can just ask for the geocontour plot of the digital elevation model and get a geographic representation here. And I can add more options to specify some additional styling rules or to express what kind of contours I'd like and many other details here. I could also plot a heat map with the same data using geodensity plot. So a geodensity plot of the Manicouagan Reservoir digital elevation model, and I've added a couple options here for styling and to specify the interpolation order for the density plot. Something else you might like to do is represent the density of data points geographically. So you can do this using spatial histograms, and there's two ways that you could express this. You could either get a smooth histogram using GeoSmooth histogram. Here I'm extracting the positions of earthquakes from the earthquake dataset that we computed earlier, or I could use hexagonal bins using GeoHistogram, and here I'm extracting the same data, getting this hexagonal histogram. And I can specify the size of the bins or the number of bins. And in the case of the smooth histogram, I could specify the interpolation order and so on. You could also plot stream plots or vector plots using GeoVectorPlot and GeoStreamPlot. GeoStreamPlot, we've seen already, can be used to plot streamlines. So here's the example with our main width vectors from earlier, where we've got our GeoStreamPlot of a list of geovectors and some additional styling options. We can also use GeoVectorPlot if you don't want these streams. If you instead just want to represent the vectors unchanged, you can use GeoVectorPlot of these main wind vectors and have the same. These are the same additional styling options, and you get this result. Finally, Wolfram Language has two functions for geographic network plotting: GeoGraphPlot for unweighted graphs and GeoGraphValuePlot for weighted graphs. I'm going to show you an example of GeoGraphPlot first. I'm going to start by creating a list of edges between continental European capitals and Rome. And once I have this list of edges, I could just represent this as a graph, not embedded on a map. And it would be kind of a boring graph. But because this is a valid graph, and because the entities that compose the graph represent valid locations, I can use it as an argument to GeoGraphPlot. And I can specify that I'd like my graph layout to represent driving directions, and I get this nice output showing me a nice illustration of the saying, all roads lead to Rome. Now, I could also represent weighted graph data. I'm not going to go into any detail about how I extract the values from flight data here, but here's an example in which first I'm collecting some information about flights that left Chicago O'Hare International Airport yesterday, and I'm counting how many flights went to a particular airport and creating a list of elements like this. So here I have an edge that goes from Chicago O'Hare to Aspen-Pitkin County Airport, and there were 3 departures that went between these 2 airports. And I just have a list of such specifications, and I can put this into GeoGraphValuePlot and get my visualization, which is interactive. I can hover over specific edges to get an idea of how many flights departed on a particular date from Chicago O'Hare to any of these other airports. We also have many functions that simplify computation with geographic data. So, for instance, if you want to get travel directions between a list of locations, you can simply say, I would like travel directions, using the travel directions function, between this list of locations, and it will return a travel directions data object which contains all of this information. You can use this object as an argument to GeoPath to plot the journey between these locations as computed by travel directions. Or you could extract the data set of instructions, and you can get these instructions in different formats. So you can get the description of the instruction to continue onto a particular road, the starting and ending point, the actual path between those locations, and so on. You can find the position on the opposite side of the Earth from a location using GeoAntipode. So for instance, here's the GeoAntipode of MIT plotted using GeoListPlot, and you can see that it's somewhere between Australia and Antarctica. We can also do what's called forward geocoding, or searching for locations by street address using find geolocation. So here's an example where I have the street address for MIT, and I'm going to use find geolocation to find that particular address on a map, and you can see that it gets us to MIT. I can also use geoidentify if I have a position for instance, the position for MIT, and I want to identify an entity that corresponds to that geoposition. So geo-identify a university that corresponds to this geodetic position, and it will return a list that contains the best matches. In this case, the result is MIT. There's also GeoNearest, which is really useful for finding locations that are nearest to a reference location. This will look for entities, so you can ask for entities of a particular type. So I might be looking for universities that are close to MIT. What are the 10th nearest universities to MIT that Wolfram Language knows about? Well, the nearest one, because I haven't excluded MIT, is MIT, and then we have 9 following that are ordered by increasing distance. We can also ask for random geopositions, random geographic positions in a particular region. So here I might have a region, so maybe Arches National Park, the boundaries of Arches National Park, and I'd like to get some random positions, 100 random positions, which I'm representing as points inside of this region. And so I can represent all of this using geographics here. This is just a small sample of functions that are available for geographic computation. There are plenty of others, including geodistance, geolength, geoarea, travel distance, travel time, and so on. I encourage you to consult the documentation to learn more about it. I'd like to spend the rest of this presentation going over some case studies showing how you might extend GIS functionality in Wolfram Language. One thing that you might like to do that isn't built in by default is using external base maps as backgrounds in geographic visualizations. You can actually specify an external source for your background using the GeoServer option in a geographic plotting function. The GeoServer option expects an endpoint for a GeoServer, for a map server, essentially. And what this is just a string template that has a slot for the zoom level, a slot for the X and the Y tile index coordinates that will return a georeferenced image that you can use as your background. This is how a lot of base maps work behind the scenes in GIS software, and all you need is the endpoint URL, which you can find lists of on the internet, and there are many free ones, and there are GitHub repositories that compile them, and so on. So here's just a few from USGS. I've made them into a little association, and the association has the following keys. So this is the list of layers that I can now represent as my additional base maps. And what I can do is if I want to extract a particular one, I can just say, I would like from my base map associations, from the USGS ones, maybe I would like the USGS hydrocached layer. And it will give me the base map specification. And I can just put this inside of a geographics call. So geographics maybe of the United States. And I'm going to specify the geo server here. And the result will be this map of the United States with the background using the GeoServer. So here's just an example where I'm mapping over the different GeoServer specifications and showing you the world maps that correspond to these different base maps. Another way you could extend Wolfram Language GIS functionality is by connecting to external API GIS services. So here's an example where I'm connecting to the Mapbox API. Mapbox provides an API for various kinds of geographic computations, and this is going to be a function for forward geocoding using their API. So it's going to take in an address and a limit that limits the number of results, and here I've hidden my little token that I can use for connecting to this API. And the way the function works is it's building a string template, and then this string template has a number of slots for different parameters, and we're filling in the string template with those parameters. Then we simply ask to import the results, so it will call that particular URL and it will return the result in raw JSON. And then the rest of this is just wrangling it so that we can represent the resulting data in a format that is valid Wolfram language code. This kind of approach can be generalized to much harder, much more complicated API calls. So here's an example here where I have a function that requests an isochrone geopolygon for a given location using the Mapbox API. An isochrone is a polygon that shows you the area that is accessible within a particular amount of time. I'm not going to explain really how all of this works because it's just the same example as the forward geocoding example, but with more options. And so once I have this, I can just say I want geographics of a Mapbox isochrone centered at the position of the MIT campus using the result computed from the Mapbox forward geocoding API function that I made just a second ago, and I want it to be the isochrone, the 15-minute isochrone for walking. So all of the area that is accessible from the MIT campus within a 15-minute walk. So building functions that connect to APIs this way is a really convenient way of expanding the toolset that you have access to in Wolfram Language. You might also be interested in bringing in remote sensing information into your geographic visualizations. And one way that you can do this is using my remote sensing packlet. One thing that the remote sensing packlet allows you to do is to connect to the GIBS service, the NASA GIBS service, and use its tile servers as backgrounds in your geographic visualizations. So how would you do this? First, GIBS data will give you a list of all of the available layers that you can access through the GIBS service. There are over 1,100 of these, and whenever they're updated, the packlet will update accordingly so that new layers are also added automatically as you go. If I'd like to get some information about a layer, I can simply take the name of the layer and ask for GIBS data of that particular layer name, and it will give me some information, including the range of dates that I can supply as an additional argument, the default date for a particular layer, and I can use this in geographics like this. So if I say geographics of France and geo server goes to GIBS geo server of that name with optionally a date option and a particular date. I'm not going to include this here. We would get this visualization using that endpoint, using that layer. So if I wanted to make an animation of different the same layer over different dates, I could do it fairly easily using this map. So here's an example in which I am making a list animation using geographic plots of plant health data, NDVI monthly data over France over a 12-month period, starting 2 months ago. If I start this from the beginning, we get this nice animation of the evolution of plant health, variations in plant health over those 12 months. In the last few examples, I focused on extending functionality through external services, but you can also build up some very powerful functionality from built-in functions and symbols. So I'm going to show a few examples, but I'm not going to focus too much on the detail of the implementations. The lesson here is really that the language offers many built-in objects to simplify the process of building complex functions. So one thing that you might like to do, which is a common task in GIS, is produce a hillshade. So we're going to start by setting up a digital elevation model as a raster using geoelevation data, and we're going to make an image from the matrix that results from this geoelevation data call, and we're going to normalize the image so that pixel values are between 0 and 1 using image adjust. Then we'll need a function that allows us to compute the hillshade of the digital elevation model. And this is the implementation that I ended up going with. The point again here is that I'm using high-level functions. I'm using these Wolfram language constructs to assemble my functionality. So I don't have to figure out how to perform a Gaussian filter myself. I can go to the documentation and learn a little bit about it. And then once I'm done, I can come back and I can just write out the expression that I need to perform this particular task. So in practice, the result is I get this shaded relief function, which is going to assume that the sun is directly north by default and at a 45-degree angle from the center of the DEM from the plane. The region is sort of represented as a flat plane, and the sun is assumed to be infinitely far away. These assumptions are reasonable for smaller areas, and the altitude angle values are expected to be between 0 and 90 degrees, where 90 degrees is the sun is directly above the landscape, and 0 is the sun is on the horizon line. So once I have this function, I can just say I would like to apply this function, shaded relief image, to the elevation data, which is this elevation raster. I enter my parameters, and I get a shaded relief image. And I can make this visualization interactive by wrapping it into manipulate. And now I can manually find the visualization that I need for a particular application, or I can just use this for exploration. I could also bring in real sun position data and use those data to represent, I could get the change in sun position around a particular location at a particular point and over a particular time range, and I could use those positions and those that information to produce a visualization here. Finally, this is just another neat example, but I can take the original digital elevation model and I can plot the I can do a 3D plot of the digital elevation model and use the shaded relief image as a texture here. So there's no shading being computed in the plot other than through the shaded relief function, and this is just being mapped onto it. So you get this interesting, this nice visualization, and it's also interactive, although it might take a second to update. There you go. For my last example, I want to focus on something a little bit more abstract and specialized. So suppose that you have a landscape image and you want to estimate its level of roughness, its level of self-similarity at different local scales. One way that you can do this is by getting the power spectrum of the image and looking at the slope of that power spectrum. And the idea is that the degree to which the slope of the one-dimensional power spectrum of the image matches -2 is a pretty decent estimate of how self-similar it is overall. We can sort of think about this as like the fractalness of that image, right? So I'll go over these in a moment, but I just want to I want to build some intuition for what's going on first. I have this image self-similarity function, which, given an image, is going to estimate how close to a slope of -2 is that power spectrum, that one-dimensional power spectrum. So the closer the value that this function returns is to 0, the more self-similar the image is going to be. So here, this Barnsley fern image returns a value that is a small negative value close to 0, and so this tells us that it's a fairly fractal, fairly self-similar image, which makes sense. And we can use this to estimate the landscape self-similarity of a satellite image. So first, I'm going to take a satellite image. I'm going to call it GeoImage. Might take a second to reload, but since I've already pre-computed this, I can just show you what's going on. So I take this image and I'm going to partition it. There you go, here it is. I'm going to partition it into a 4x4 grid. And I get this partition so that I get sub-images, and then I can map my self-similarity function, my image self-similarity function onto all of these squares, and I can get a value representing the self-similarity of this patch. And I can do this at different scales. So I can start with um, some of these patches, and I can get an estimate of half a square mile landscape patches and the self-similarity of those patches. Or I could subdivide each of these squares into 4, and I could get the next level of self-similarity, or subdivide each of these into 4 and get the next level, and so on. And what I need to keep in mind here is just that at some point I'm going to be computing self-similarity measures on very low resolution images, and so the information that I get from that is going to be less meaningful. But the point is that I can look at different scales and see sort of locally how fractal are different patches of this landscape. Okay, so now I think we're ready to kind of talk a little bit more about how this is all put together. Again, I don't want to focus too much on the implementation here, other than just pointing out that this is built out of Wolfram Language without any calls to external services or any calls to external languages or any other kind of shenanigans. This is just this is building an image in which each pixel is the distance from the center of the image. The pixel value is the distance from the center of the image. Then this is computing the unscaled image periodogram of an image. Um, then this function is binning together values at the same distance from the center of the image, and then using that information to reconstruct the power spectrum of the image, the one-dimensional power spectrum of the image, and then I can represent those data in a list plot, so I can get the power spectra of the different channels of the image represented. And then finally, I have this image self-similarity function, which will take the power spectrum data and estimate the fit to a slope of -2, estimate the distance to a slope of -2 of that power spectrum using a linear model, and will return the result. And as with the previous example, I'm using things like linear model fit or image measurements. I'm using image array measurements, numeric array, delete cases, thread. I'm using these high-level constructs to simplify the process of expressing this complicated set of ideas that I need to put together to make this work. I'll leave you today with some helpful resources for learning about GIS functionality in Wolfram Language. A great place to start if you're a beginner is the Language Core Areas page on our website for geography. There's also a really good gentle introduction in the Wolfram Language Learning Center on geography and GIS. And then for more detailed guides, you can look through the Wolfram Language documentation and find many useful pages about maps and cartography and other GIS tools, other GIS applications. If you're starting out and you're very new to the language, you can also head to some great resources to look into the documentation center and the elementary introduction to the Wolfram language, or the fast introduction for programmers if you're already an experienced programmer in other programming contexts.